Okay, we're at the top of page 20, acids and bases. They fall under the category of electrolytes. It turns out that acids, bases, and salts are electrolytes. And what that means is if you take either an acid or base or a salt and place it in water, it'll be able to conduct electricity. All right, water on its own is a poor conductor, but when you spike it with salts, acids, or bases, because they produce ions, they end up lighting a light bulb. They don't generate electricity, they conduct electricity. All right, so the key thing is that they have in common is that electrolytes produce ions, just like Gatorade, if you recall, supplies your body with the electrolytes that you deplete as you exercise. So electrolytes produce ions. And ions in water conduct electricity. Non-electrolytes, on the other hand, give you no ions. And typical non-electrolytes are your sugars. You probably recognize glucose. This would be sucrose, the dimer of glucose. And you should also know that alcohols are non-electrolytes. They look like bases, by the way. We'll discuss that in a second, but just look at that right away. The bases are metal hydroxides, not some carbon hydrogen with an OH. So don't confuse alcohols with bases. And alcohols are soluble in water, but they don't produce ions, and therefore they are non-electrolytes. You should always know 2 sugars and 2 alcohols by heart, even though the alcohols are listed in Table R. It's good to know these. All right. Now let's focus on acids and bases, because salts, ionic compounds, were covered in the bonding unit. Remember, this happens to be table salt, but any ionic compound, any metal-non-metal combination will give you ions, will be a salt that conducts electricity. All right, and now let's focus on acids and bases, and you should turn to table K and table L. Table K are your common acids, and table L are your common bases. And what all the acids have in common, as you can tell from their formula, is that acids produce hydrogen ions in water, H plus aqueous. And what the bases have in common, as you can tell from their formula, looking at table L, is that they produce hydroxide ions in water. Now the NH3 happens to be a weak base, and you might be wondering how are you going to get an OH out of here. But the NH3 is also known as, aka, ammonium hydroxide. And how that occurs we'll discuss later on. All right, so now some properties that distinguish, that identify acids versus bases. All right, acids have a sour taste. So anytime you've had vinegar or lemon, anything sour, that's because of a weak acid that's present. Although the taste test is not a good idea to tell whether something's an acid or not. And bases, on the other hand, are bitter. And they also have a slippery or slimy feeling in between your fingers. And then as far as other properties that distinguish acids from bases, they change the colors of indicators. We'll talk about the indicators later. Most common being litmus and phenolphthalein. Acids react with metals, except coins. All right, so the coins meaning we used to make coins solely of copper, silver, and gold at one time. But you'll know which metals don't react by going to the bottom of table J. And table J, it's an activity table, but underneath H in table J, you can refer to that now, you'll see that copper, silver, and gold, the 3 bottom ones, do not react with acid. All right. Acids have a pH that is less than 7. Bases have a pH greater than 7. We'll talk about that in a minute. All right. And then also, if you look at table K, there's a reason why the first 3 are HCl, HNO3, and H2SO4. The names are as listed in Table K, hydrochloric, nitric, and sulfuric acid. These three listed on the top of Table K are strong acids, and the bottom ones in the Table K are your weak acids. So your strong versus weak. Now, how that works out experimentally is that if you were to take, let's say, HCl, let's do that. Let's take a test tube that contains some HCl in it. So you have 1 molar HCl. You place a piece of, let's find a metal in Table J that will react with acid. You'll see there's a lot of metals that do so, but let's place a piece of magnesium. What you'll see is bubbles. In this case, a lot of bubbles, because hydrochloric acid happens to be a strong acid. And those are bubbles, of course, of hydrogen gas. Now, to contrast a strong acid with a weak acid, why don't we take the bottom of Table K, the ethanoic or acetic acid. Let's place that here. Let's make sure it's a 1 molar solution also. So, and that acid at the bottom of Table K can be written 2 ways, recall, as HC2H3O2 or CH3COH. And we'll talk about why that is in a second. But let's write it as HC2H3O2. So we have acids of equal concentration, and we'll put some magnesium here too. And in the case of the weak acid, you'll see much less bubbles. So the relationship that you need to get at is between, as far as strength and rate of reaction, and the amount of bubbles, in this case, of hydrogen. So the stronger acid, the HCl, will react faster with the magnesium, give you a faster rate, and as a result, you're going to see more bubbles of hydrogen being produced. Okay, a note on the bases. In the top of Table L, you have 3 bases listed there. Again, the top 3 there are strong bases. And the way you could recognize a strong base is you'll see what they have in common is that they have metals from groups 1 and 2 in your periodic table, sodium, potassium, and calcium. And so you think of the strong bases as being metal hydroxides of groups 1 and 2. And the exception being, of course, the beryllium and magnesium. Beryllium hydroxide and magnesium hydroxide are relatively weak bases. All right, and then underneath these 3 metal hydroxides, you have the ammonia, which is your wimpy or your weak base. So ammonia and amines in general are weak bases, and we'll talk about amines later on in the organic table, but might as well draw an amine right now. So how about we write CH3, CH2, NH2. Notice the similarity between this amine, which is an organic base, and the ammonia. And so these are both weak bases. And then the thing I was going to tell you about here, about acetic acid, let me just warn you here. I'll just erase here. Put a note here about acetic acid. Notice how the acetic acid, like the carbonic acid, can be written both ways. The acetic acid is written like this to remind you that acetic acid is an organic acid. And when we go over organic chemistry, we'll deal with this. So you could write it either as HC2H3O2 or CH3COH. So the hydrogen here is the one that's deprotonates, that breaks off, and that's the hydrogen here that breaks off. All right, so remember this as acetic or ethanoic acid. Put a star by that because, first of all, it can be written both ways, and secondly, it looks almost like a base. It could fool you into thinking it's a base because of the OH. But again, bases have metal hydroxides, not this. All right, and like I said before, one more thing. I mentioned that acids react with metals, and notice I mentioned nothing about bases reacting with metals, because typically they don't. Of course, there are some bases that do, but as far as this course is concerned, let's forget those. Okay, and then let's look at the pH scale. Now, you probably went through this in a living environment, the pH scale. And the pH scale, if you recall, ranges from 0 to 14. All right, and from 0 up to 7 is acidic, the acidic range, and from 7 on, 7.1, etc., anything greater than 7 would be the basic range. All right, now in the acidic range, the lower the number, going from 6, 5, 4, 3, 2, the more acidic. So why don't we put that here? More acidic is that way. And the higher the number, going from 7, 8, 9, 10, etc., the more basic a solution is. And the point to be made about the pH scale is all solutions contain H plus, all aqueous solutions contain both of these ions, H plus and OH minus ions. A solution that's acidic is a solution that has more hydrogen ions than hydroxide ions. And a solution that's basic is one that has more hydroxide than hydrogen ions. And a solution that's neutral is a solution in which they're both equal. So 7 is your neutral point, and only 7. If you want to get a relationship between acid strength, hydrogen ion concentration, pH, then we could go with the stronger acid. Stronger acid is going to have a higher concentration. Remember, this stands for concentration here. This bracket, or in other words, molarity, and a lower pH. And we're going to have to explain why that is, because that's a little confusing. One other note I put here is that a hydrogen ion in water, an H plus AQ, technically speaking, is a hydronium ion. And what they mean by that is this. Let me just draw that for you here. A hydrogen ion, you see, is a very reactive species. And so the hydrogen ion is hungry for 2 electrons. And so a hydrogen ion in water would not stay by itself. It would instantly latch on to the 2 electrons that are here, and you'll end up forming the H3O plus, the hydronium ion. That's an interesting kind of bond here because unlike the other oxygen-hydrogen bonds in which the oxygen is providing 1 electron and the hydrogen is providing 1 electron, so they're sharing, here the oxygen is coordinating the bond. It's providing both electrons to be shared, so you can think of it as the hydrogen is latching onto those electrons, and as a result we form this polyatomic ion, the hydronium ion. So that's a good one to keep in mind, since a lot of times they ask questions about the hydronium ion, which really means a hydrogen ion in the water. So you could change it with this here. You could say the higher the concentration of hydronium ion if you wanted to. Since they are synonymous, they mean the same thing. Okay, let's look at the pH scale and understand why a lower pH number means a greater concentration of H plus. Let's turn to the bottom here of this page. Again, all solutions contain H plus and OH minus ions, all aqueous solutions. And it's the relative amounts, what there is more of, that determines whether the solution is acidic or basic. So now, when they tell you that a solution has a pH of 7, the easy way to think of pH is the power of the hydrogen. All right, so if the pH is 7, that means the concentration, remember this is concentration, the molarity of the H plus is 1.0 times 10 to the negative 7. And since all solutions contain both ions, it turns out if the H plus concentration is 10 to the negative 7, then the hydroxide concentration is going to be the same because of something called the Kw, the water constant. But you'll learn more about that in AP chemistry. Just it's important to know that these two exponents are always going to add up to negative 14. All right, so in this solution, since the concentration of H plus and OH minus are the same, you have a neutral outcome. Now, if the pH is 5, the H plus is 10 to the negative 5, can you guess what the hydroxide will be? Okay, so that would be 1.0 times 10 to the negative 9, since they have to add up to negative 14. And in this case, the H plus is greater than the OH minus. Remember, with negative exponents, all right, the smaller this number, the greater the magnitude. So in this solution, we have an H plus greater than OH minus, so this solution is acidic. Now, about the point I made before. Notice as we're going from a pH of 7 to a pH of 5, pH value is decreasing, pH number is decreasing, but the concentration of H plus is going from 10 to the negative 7 to 10 to the negative 5. So that's a greater quantity. So the reason why, as you decrease the pH number, it's a greater amount of H plus is because we're dealing with negative exponents. The pH scale is a negative exponent scale. All right? Now, let's work this one backwards. Here we're told that the hydroxide is 10 to the negative 4. So that means the H plus has to be 1.0 times 10 to the negative 10, since they add up to negative 14 always, which means the pH, the power of the H, is 10. And so here the hydroxide is greater than the H plus, and so this solution is basic. Bases make solutions basic, just as acids make solutions acidic. And then if the pH is 3, can you fill in the rest here? So yes, the H plus is 1.0 times 10 to the negative 3rd. The OH minus, since they have to add up to negative 14, is 1.0 times 10 to the negative 11. Negative exponent, smaller is greater. So this solution, since it has more H plus than OH minus, is also acidic. Now, there is a tenfold difference between consecutive pH units. Now, what do we mean by that? All right, well, that means is if the pH were to drop from 5 to 2, we know we're going to a greater concentration of H plus, but how much greater? Well, the difference is 3 pH units, so it would be 10 to the 3rd, which is 1,000 times greater. All right, let me elaborate on that, because that's a little confusing. Some space down here. So let's draw this out. So you got pH 5, 4, 3, and 2. So what I'm saying is, as we go from pH 5 to pH 2, yes, pH 2 has a greater concentration of H plus because, as we said before, we're dealing with negative exponents, and so a smaller number means a greater quantity. But how much greater? Well, since there's a tenfold difference between pH units, as you go from 5 to 4, it's 10 times greater. And then from 4 to 3, 10 times that. And then from 3 to 2, 10 times that. So it's 10 to the third, which is 1,000 times greater. Another way of doing that is, if you're an exponent person, which most students aren't, you're comparing 10 to the negative 2 to 10 to the negative 5. Negative 2 minus a minus, remember when you divide by exponents, you're subtracting, means you end up with a 10 to the third result, which also means 1,000. All right, so going down, again, we're saying it is more acidic. And now we can tell you how much more acidic. Now, on the other hand, if you were to go up in pH from 8 to 10, now you're saying you're going for a solution that is more basic. You're increasing the concentration of hydroxide. And so the difference is 10 versus 8 is 10 to the second power. It's 100 times greater, the concentration of hydroxide, as you go from 8 to 10. All right? All right, so we've come to the bottom of this page, and it gets a little mathematical, the acid-base unit, especially when we talk about titrations. So you're going to need a calculator for the next page. All right, so we could discuss that. So we're turning to the top of page 21, and I'll see you there.